Welcome to our NPTEL lectures on the power quality improvement technique. Today is a passive filter design, the second lecture on it. So, please recall, so we are left here. So, we have calculated the value of the capacitor and now want the value of the inductor. So, to trap the nth harmonic current, the inductance of the order of the filter is Ln equal to n square omega square Cn. So, the series resistance of the inductor for the nth order is Rn, and that value will be n omega Ln by Qn. So, Q is something that you will fix and you go back to the value of R, and where Qn is a quality factor of the inductor of the nth filter, and which is normally considered to be 10 to 100, but generally it is 30 to 60. Now, how you design an inductor? Now, you get the value, let us say L and R. So, then there is a few issues. Now, inductor generally will have a rolling over effect. So, generally if you have the value of the inductor, that is Ni, the ore state, and the flux. So, you will find that after some time essentially it is B by H graph, and you expect that it will have a saturation at this point. After saturation, what happens? If you increase the value of this Ni, definitely flux is not going to increase, and thus the value of the inductance will decrease. So, value of inductance will have a rolling over effect after some value of current. For this reason, we require to specify. So, at a no load inductance, which you will measure, what should be the value? Full load inductance, what should be the value, and generally it can be able to overload it, and what should be its value. And accordingly, you will choose the number of turns. So, ultimately you know that number of phi is essentially is reluctance, ultimately n phi by I. So, what is phi? Phi is n mmf by reluctance, where it is mu 0 mu r, where L into generally you may have a air gap by area. So, you can see that II cancels out most of the cases, and ultimately L depends on the geometries of it, and ultimately L will be proportional to n square as long as I is in a linear region. So, you know the number of turns now. From the number of turns, and you have chosen a core and where you will host this wire. So, that length you know, and thus you if it is 2a into b, this is the periphery of this coil, into number of n gives you the length of the wire. So, then your R value is fixed, that is rho L by A. Once this A value is fixed, you have to choose the value of the A from the AWG table, and thus you get the desired resistance. In that way, we will calculate the value of the resistance, and sometime when there is see that there is a mismatch in between, you may require to feed a external resistance to it. Of course, you can reduce the Q factor. By that, if you want to increase the Q factor, then of course, you have to increase the area of the wire gauge. Now, for designing the second order damped filter, generally it required to be tuned and it should be optimally damped. That means it is very close to critically damped. We should not have over damped entities. So, that will make the system sluggish. The response time will be less. So, the second order damped filter, the filter parameter, the CH, LH and RH are also calculated by using the same equations. Now, that comes to the next point. However, the next dominated harmonic is considered as a next value of n for the high pass filter, and its quality factor QH of the inductor of the high pass filter is considered between this. So, let us switch over again and next. So, you will have a small inductor and a capacitor and a resistance. So, and ultimately you will this is if you have a step response, generally if it is a damped circuit, you know that this is a case of the under damped and this is a case of the critically damped. So, you will have this entities, and for this reason you will eliminate all those higher order frequency. You will set the cutoff frequency at higher frequencies, let us say after 11, 13 and so on. That will all ultimately it is a band pass filter if you look at the series, but it is connected in shunt that automatically gives you the saving from the high frequency which is connected parallel to it, and thus what happened, and you require to put the value of Q in between 0.5 to 5. And now you know that the S square plus 2 zeta omega n plus omega n square, where omega n is under root of LC. So, and you want a transfer function as under damped. So, there is a condition of the zeta. So, zeta should be generally we require to keep the zeta value just little above 1, and accordingly the Q factor required to be designed and having a Q factor range 0.5 to 5. So, this is a way generally design the high pass filter. Similarly, this procedure may easily modify to design the series passive filter. The logic will be just different. You will ultimately block it. Here you are bypassing it, there you will be blocking it. Now, let us come to the important aspect. From 1984, once Akagi proposed the reactive power filter solutions, we moved today's this course will run in 2020. So, we have moved 36 years. So, by that time now it is a domain of totally the active power filter, and active power filter also is a proven solution, and we do not require to look back than the passive device, and the cost of this passive device is increasing because cost of the capacitors, as especially in India where inflation is being placed, it is increasing, whereas by defeating inflation cost of the switch, because of the patent issues, cost of the switch was high and gradually it is decreasing relatively. And for this reason we are now looking after the active solution, but we cannot replace the passive filter totally, and thus we have a combination of the hybrid filtering. We will discuss it in detail with the shunt active power filter, active filter, what is the role of the passive filter. So, anyway, now let us discuss what are the limitations of this passive filters. So, the passive filters are not adaptable in varying system condition and remain rigid once they are installed. For example, you want to put a filter in a weak grid, we also allow the variation of the frequency once we have discussed the standard, and that is allowable range of the varying frequencies. What you were saying, it is a 50 hertz. Nowadays, due to the power grid corporation, most of the problem has been solved because of the huge inertia in India. Almost frequency is very much constant, and it varies only a very low, less than 0.25 hertz from no load to the peak load. So, but where the deviation is quite high, there it will not function properly, because you have tuned to the 250 hertz. Definitely, then at if it is a 2 hertz variations, automatically that will be a 10 hertz variation to the fifth harmonic. So, at 260 it may not work that properly if you have put the sharpness quite at this point of the 250. So, it will not work, and it is not flexible to the change in the frequency. Thereafter, changing the operating condition of the system. For example, operating condition means it may have a sags, it may have a swells, and thus the rating of this voltage may change, and there it may require to be tuned properly, and whatever desired reactive power compensation you wanted, you do not get it. Moreover, the system may result in the detuning of the filter and may cause the increased distortion instead of that. So, that will enhance the problem instead of the mitigating the problem. The design of the passive filter is reasonably affected by the source impedance, because you are changing the source impedance. For an effective filter design, its impedance must be less than the source impedance. Otherwise, the entities will not be sync into that, because are connected in a passive. Once you want that, and thereafter you got a source inductance. So, ultimately fifth harmonic impedance should be less, then only it will sync there, otherwise it will go there, as simple as that. It may result large size of the filter, as I told you, because you want the sharpness of the resonance higher, the value of the coil you chosen for the inductor may require to be higher. In a stiff system with low source impedance, generally it happens in a stiff system, the source inductance is quite low, which may results overcompensation of the reactive power. Ultimately, you live in a capacitive region. So, that may be one of the problem of the passive filter. The overcompensation may cause the over voltage, because once you are compensating, terminating the line with the capacitive bar, the voltage will swell up. Over voltage on switching in the under voltage on switching out the passive filters. So, what happens? The overcompensation may cause over voltage on switching on. Once you switching on this nonlinear load, you have to switch it on this passive filters also, that will jump up the voltage, and once you withdraw, there will be under voltage switching of the passive filter. So, voltage switching will take place due to that overcompensation. The passive filter are designed with a large number of elements, because you have seen the capacitor bank, I have shown you some pictures of the real capacitor bank placed, and it occupies a huge place itself. That is also a good amount of real estate cost. Think about if it is placed to the commercially viable place, so that has a good amount of the real estate value. So, that has to be catered into the system, not only the cost of the bill of material elements, and loss and damage of the some element may change, that is detuning. I have not talked about it, detune it is another issue. Some of the element may change the resonance frequency, and that may increase the distortion. So, if somehow the value one string of the capacitor is damaged partially, then the value of the capacitor is changed. So, instead of the attenuating fifth harmonic, it will attenuate, let us say it has been tuned to 3.8. So, that leads to the distortion of the voltage. In case of the large filters, the power loss may be substantially high because of the resistive element, because you want that some value of R to be there. So, some value of R to be there, and R value gives you the losses, especially in case of the series entity. And another problem is that parallel resonance, due to the interaction between the source and the filter, can cause amplification of some of the characteristics of the non-characteristics harmonic. So, since it offers anti-resonance, so it will offer very high impedance to a particular frequency, that may disturb the power system, which was not at all an issue in a particular case, because it will aggravate because of this parallel resonance problem. There are another big challenge is the size of the damped filter becomes large in handling the fundamental and the harmonics frequencies. So, this is quite big issue, because once you have a damped filter, because you want that you should have LC fine, thereafter you want that it to be damped. So, that takes lot of spaces, because current rating has to be matched, it is not that simple ceramic resistance. So, for this reason that also require a bigger size for damping. The next is the fundamental effect such as aging. This is something quite problematic, because it will detune and derate. So, one problem will be detuned. So, instead of the fifth harmonic, it will compensate some other harmonic, and the value of this capacitor also will come down. So, effective compensations of the reactive power also be less. Due to such aging, deteriorations and the temperature change detunes the filter in a random manner. So, problem lies in evening, it will operate at some frequency when temperature is less. In afternoon, it will operate at some other frequencies. In some cases, even the presence of the small DC component, generally it comes into the picture because of the triggering angle failure of the thyristors, or little mismatch between the triggering angle of the thyristor. The harmonic current may cause saturation of the reactor filter. So, inductor may saturate, the flux value will saturate, and value of the inductor will degrade much. So, current once flow, no change into the current will be occurring. So, thus this is one of the biggest problem, and thereafter special switching is required for switching and the switching out the passive filters to avoid transient. We have discussed in detail, we have a short of time here, for this I cannot discuss here, inserting capacitor in the fax devices. Please see that applications. Once you insert a capacitor, series capacitor SVC, so where you can enter if it is already that capacitor, generally you cannot always have that discharging totally. So, you require to enter the capacitor bank when this it is sinusoidally varying, when the supply voltage and the capacitor voltage matches, and also you generally take it out, because there is a problem, because capacitor current and the voltage are 90° phase shifted. So, it is not advisable to take it out the zero crossing or at a peak, because once zero crossing is others peak. If you say that look I will take it out in the zero crossing of the voltage, fine, but current is at peak. So, inductor will create a problem. So, for this reason we wanted to generally what we do, we wanted to take it out or insert these filters when voltage levels are same, then we will insert with the nominal value of the current, not at the peak value of the current. So, that is something we require to do. Placing is not blindly to be done, otherwise you will have a transient and the sustained oscillation, and to remove the sustained oscillation you require to tamp out. Another problem is that the grounded neutral, this really happens in the star connected network, the grounded neutral of the star connected capacitor bank may cause amplifications of the third harmonic current in some cases, and thus current will flow and you have to, and third harmonic voltage will build up into the system. So, that we require to take care about it. Another issue is that special protective and monitoring device are required, because mainly this transients, and also if it is surge affected and if it is having other problem, so you require to bypass to the system, and for this reason also we require to have a protective and the monitoring relays to ensure that it is functioning properly. Parallel resonance with the supply system is a common problem in a passive filter, shunt passive filter. So, that is the anti-resonance, and thus it offers high impedance. Your admittance is minimum, impedance will be high. So, what happened then? With the resonance of the supply system, this resonance may happen between the inductive reactance of the supply impedance and the capacitive reactance, and sometimes occurs with the leakage reactance of the transformer and the capacitor bank. This is totally unknown phenomena sometimes. Of the shunt passive filter or the capacitor used for the power factor correction. So, this is also one of the element that will solve some problem on gate and give you in assignments, and you will see that how detrimental it is. And moreover, the parallel combination of the inductive reactance of the supply and the capacitive reactance of the passive filters offer infinite parallel impedance, that is also very detrimental at the frequency FR when these two reactants becomes equal. So, that is and so we say that this frequency FR is known as the parallel resonance of the frequency, and this behaves like open circuit compression. You have condition, you have studied the waves in open circuits, and thus it will be open circuit for the harmonics. So, any frequency of the harmonic producing load connected at the PCC at the close to the resonating frequency, if it is anti-parallel resonance, a severe voltage distortion because of the reflecting wave, and that is not a fundamental at that particular frequency, and the harmonic current amplification may occur that may result malfunction of the relay sometime, and it may trip. So, this situation we require to avoid, and we require to the relay should have, now the digital relay have that sensitivity to operate and monitor at this condition. And this is one example of it. This amplification of the harmonic current may be many times of the sufficient and it may be sufficient enough to blow out the fuse or cause the circuit breaker to trip or relay to malfunction. This is a 50 S supply, they are at a transformer, they are at a PCC, you have a nonlinear load. These what happen, this leakage reactance and this capacitance may set to a resonance, and if that resonance is generated by the fifth harmonic, then there will be amplifications of the fifth harmonic resonance, and high fifth harmonic current will flow, and it may cause to the malfunction of the relay. So, and this equivalent circuits can be like this. So, you have a RSXS, that is a source part of it, thereafter this is the leakage part of transformer, and this is a filter, and ultimately if you combine, you just neglect this part because being negligible source inductance in a steep source. So, XTRT and LFCF let us have, and thus what happen, the total impedance of the equivalent circuits omega A can be this, and it may be a resonance for any particular frequency accidentally. So, Zi can be cancelled wide range of the frequency to locate parallel resonance frequency at which the impedance has the maximum value. Under the parallel resonance, the denominator of the impedance Zi must be have a minimum value. It will be minimum value at the frequency omega r, and when the inductive reactance is equal to the capacitive reactance. So, equate it. So, you get the value of the omega r, and omega r if it is fifth harmonic, great. The parallel resonance phenomena can be avoided by shifting parallel resonance FR value to less than the lowest order harmonic current presents into the harmonic producing load. So, that is the one way we require to check. So, it should not match. This shifting of the parallel resonance frequency FR to much lower frequency than the harmonic present into the load avoids the amplification of the harmonic. This is the way this problem is been tackled. So, you should not be close to the harmonic generating frequency. This is also, and this is also one of the reason why tuned filters are tuned at 5 to 10% lower than the actual harmonic to be reduced into the system, and some effect may come from the leakage reactance, source inductance, stray capacitance. So, it will add up your value. Thank you. This is the how we proceed with the passive filter. Thank you for your attention. I shall continue with your discussion with the other topic of the power quality.